So many times when architectural acoustical issues are to actually create isolation of sounds so that we can have meeting rooms with privacy. We can have rooms that are quiet enough that it's easy to listen to someone who's speaking or making a presentation. Many times we're looking at building components, walls, the constructions of assemblies that help us to isolate sound. So this idea of building materials having a sound transmission class is something that we talk about a lot when we talk about acoustical building materials. So I brought up this chart. This talks about sound transmission class over here, and you can take a minute to either pause it or read it as I'm talking. But we have these built forms. For instance, a single layer of drywall on each side of a wood stud has a sound transmission class of 33 and down at the porous level. And then the best performing things are it's up at the top, concrete block wall, painted, so there's no permeability to it, with drywall on it, then a steel stud wall on each side, and insulation in the cavity. So these are to create a very high level of sound isolation between two rooms. And then this is the same chart, and I've associated that with this idea of what the STC value is, and then what could be heard between two rooms. So if you had a glass panel between you and the other person in another room, and it was quiet, you could hear somebody speaking. And then if it was 60 plus superior soundproofing, you could be torturing someone in a room and the person next door wouldn't be able to hear it at the most extremes. So there are ANSI standards for spaces. So we have these values that were talked about and the construction system. And so we can build up a STC 45 wall in a variety of different construction methods. So they're not telling you how the wall needs to be constructed. They're telling you how it needs to perform. And then in this case, these are performance criteria for sound isolation between adjacent rooms. In this case, it is part of an ANSI standard for a requirement in schools. So this is I guess to punch this home a little more, this is where we as designers will spend a lot of our time talking about these sound transmission class construction systems and where they're required by code, and also where they're required by just the logic of us trying to create proper performing acoustical workplaces or homes or residences. There's another way sound transfers, and that's through this idea of impact. Imagine a wood floor. If you've ever been in an apartment where you have someone living above you and they're walking across the floor in hard shoes, high heels, and you can hear every motion that they're making. And the sound is being transferred through the physical impacts of the shoe on a hard surface. And so we a lot of times try to create surfaces that deaden that impact, that physical impact on the surface from being transferred to the next space. This is really important when we talk about things like now with wood being very popular construction, heavy timber construction. Wood floor systems are sometimes solid between the floor and the ceiling, and other techniques need to be added to help to isolate this transmission of sound from just foot traffic and moving of equipment. We talked about this, that's the physical transfer. And then we have the acoustical transfer through our walls. And I put this illustration up again to talk about this idea of the noise reduction class, the ability of a specimen to perform in reducing the sound in a space. And one of the things that we as designers and architects will always concern ourselves with is this kind of a relationship. A workplace where we're trying to control the transmission of sound between two workplaces so that people can have some degree of privacy or ease of communication with somebody on the phone or in other discussions. So we talk about these ABCs. We want to absorb the sound, by an acoustical ceiling that soaks up sound, block it by a physical barrier, and then cover it with sound masking. So that sound masking can be air going through the HVAC system. It can be white noise, which is sound that is just created um, by speakers generating a noise tone that helps to mask overall sound. Or it could also be a bunch of people talking at the same time, where it makes it hard to distinguish any single conversation and it creates just a general hum in the room. Once again, OSHA, Occupational Safety and Health Administration. I said hazard, it's Health Administration. So we have this idea of permissible noise level and worker exposure. So, and these are really actually quite painful standards. These are very high pressure levels, but you'll notice that um, you can have a worker in a room at 90 dB for 8 hours a day, but as we get up to 115 dB, we're talking less than 15 minutes of exposure to it, permissible noise exposure. And I think that's probably without hearing protection. So this idea of a logarithmic scale and these sounds getting very strong very quickly. So we have a 10 dB, the sound of breathing. Um, City traffic at 70 and 80 dB. Remember that work environment, the sound of a hairdryer at 90 dB all day long. And then when we're up in the jet engine sound at 130 dB. And the threshold of pain is 140 dB. So when we talk about these noise levels, these are hugely significant. It's impossible to carry on conversation, basically to do anything else but wait for that sound to pass. And here's that same idea of a logarithmic scale. So the increase to 60 dBs with an air conditioner on, 4 times louder in this measurement here. So we have noise apartment at 40 dB, and then when we go to 60 dB, it's 4 times louder. So it's a change of 20 dBs, but it's a 4x increase. So I thought this was a good graphic for this idea of noise control in public spaces. We are always faced with this. This is actually kind of changing. We're probably after our pandemic, we're looking at reducing the density of office spaces. But up to that point, it was usually the more people in a space, the better. And so we were always concerned with this idea of noise isolation, ways to cut down on the amount of noise in the environment to allow people to have conversations, to reduce distraction between workers. So a lot of things went into the thinking of these open office environments to improve the acoustics, even to the concept of saying open office concept really don't work, and we need private office spaces. So this is one of those interventions again. So I showed you this idea of a divider system to control noise. Funny thing is now that'll probably be the divider system will also be the system that is intended to reduce transmission of infections in office environment going forward. Another interesting change with our ideas about pathogens in public spaces. Densities of restaurants will probably change. And some consideration will probably be given to this idea of noise because of the feelings of anxiety in tightly packed situations. So it's been up to this point, noisy restaurants have been an indication of a busy, positive space. Restaurants have very little incentive to reduce noise. It always seems to benefit them. And so now we may have an attitude where restaurants want to create a much more calmer environment. We may start looking at new kinds of acoustical interventions in restaurant design. And that all leads us to what we'll do in our lab project, our section, where we'll make some interventions in a wall construction between our bathroom, some absorption surfaces in our ceiling planes and our wall planes, um, to kind of cement home this idea of thinking about our built environment as an acoustical environment at the same time. And this is a nice resource. This is paper linked. So if you click on this, it'll take you to that PDF. I thought this was an excellent resource because it talks about all kinds of, excuse me, I'm going ahead on slides here. It gives ideas about doorway placements and transmission of sound, placements of heating ducts, because these ducts are open, they can transmit sounds from offices to offices. So the idea of designing layouts can be interesting. So this acoustical assembly from USG, a gypsum board manufacturer, I thought was a very useful resource. I think this is where I got the wall construction data for the project that we're going to do. And then there are many other resources on the internet. I think this one's also hyperlinked to sound absorptions materials. And why I think these are valuable is they're also have visual value to them to improve the appearance of our interior built buildings. So that's available to you. And we're going to actually make this acoustical surface in our lab. And then, you know, I guess to leave it, or at last, this idea of architectural interventions opens up a whole space for all kinds of creative crafting, especially when we look at the idea of the ceiling environment. The ceiling environment tends to be one of the places ripe for the easiest amount of intervention. Soft materials that absorb sound are protected from human contact. So if you wanted an absorption surface on a wall that was soft, you'd have to worry about wear and impact on it. On the ceiling, it's virtually untouchable. So we can do a lot with it. And it's a whole space that we can carefully craft and sculpture the interiors. And sometimes it goes a little bit overboard, but this is a doctor's office in downtown Buffalo, a new space. And this idea of ceiling clouds, we worked on this a little bit in computer viz. But we have an open ceiling plane up above, and then we've introduced these sound clouds with acoustical materials. They allow us to place our lighting systems in. It could be our fire suppression systems. And then if you look back here, it helps to mask the appearance of our HVAC systems. And that covers it for acoustics.